Okay, today we're going to be continuing on with flow over external bodies or external flows. And last class we focused on drag and over bluff bodies. And today we'll start to move more into flow over streamlined bodies or viscous flow around an airfoil. In particular, kind of start out with this figure that we have here, which is flow over an airfoil. You can see we have streamlines that are coming in from a uniform flow that's upstream of the airfoil. And as you know, we have a stagnation point located at the leading edge. Typically, we'll have a laminar boundary layer. That's what the LBL stands for here, that starts to form after the leading edge, both going from the lower and upper side. And then at some point in time, we'll get turbulence, and the boundary layer will become thicker rapidly and move out away after the transition. So we'll have, again, laminar boundary layer, turbulent transition, and then this region here, which will be the turbulent boundary layer. Down near the trailing edge, we'll have a separation point. And the more streamlined the airfoil is, typically the smaller that region of separation is. And then down here, we'll have this viscous wake region that exists. And generally, this is kind of the pattern that you would expect for flow around an airfoil. If we think about the drag on an airfoil, which we've kind of talked a lot about drag so far, here's a plot of the drag coefficient as a function of the thickness to chord ratio. We'll talk about this a little bit more in just a second, but since we were talking about drag last class, I think this is an appropriate way to start it. So if we think about an airfoil, then here, the chord length that we have, so this is from the tip to the tail, that's our chord length, and then the thickness is defined here as the maximum and minimum thickness. As that ratio changes, the ratio of whether we're dominated by pressure drag or by skin friction drag is going to change. So if we have a very slender airfoil, so that is that slender would mean T over C. That is the thickness to the chord length is small. So we call that very slender. In those cases, that would put us towards the left-hand side of this figure. And you could say maybe if we look at a thickness to chord ratio of, say, about 0.1, then you would see in this case that the drag coefficient is dominated by skin friction drag here, and there's much smaller pressure drag. And the total drag, of course, is the sum of the two. So given these three different curves that show the total drag, the skin friction drag, and the pressure drag, what happens is, as we move to the right of this diagram, effectively, we go from a very slender airfoil to a thick airfoil. And that's when T over C is going to get very big to the right-hand side. And in that case, our airfoil eventually starts to kind of look like a cylinder, say, for example, or a sphere. And we know that a sphere is dominated by, or a cylinder is dominated by, pressure drag at high Reynolds numbers. And so what happens is then our skin friction drag starts to go down and our pressure drag goes up. And what you'll see is that, somewhere for a symmetric airfoil like we've seen here, somewhere maybe at a thickness ratio of about 0.25 or so, that's where the minimum total drag exists. And it's the crossover point between where you have a pressure drag dominated situation and a skin friction drag dominated situation. So if you think about in your head, what is a classical skin friction dominated type of flow situation? Well, that would be flow over a flat plate or a very, very slender airfoil. If you think about what's a pressure drag dominated form, that would be something like a bluff body, flow over a boxy vehicle, flow over a cylinder, flow over a cube. These are going to be dominated by pressure drag. So those are two kind of objects that we're looking at. And depending on the shape of our airfoil, it could be either. For an airfoil and any type of object, we talk also about streamlining. And streamlining is really important because what we want to do here is we want to reduce the pressure drag, okay? And based on what we just saw there a second ago, it gives us a hint on what we want to do. So we want to reduce the pressure drag. And by doing this, essentially what we're trying to do is we're trying to reduce these regions where we have an adverse pressure gradient, where dp dx is greater than 0. Okay, so we want to either minimize its size or the magnitude and therefore avoid separation. So how do we do that? Some of the different things that can be done. You can add fairings. So what we mean by fairings are cowlings. So if you have, say, for example, some object that has a very non-aerodynamic shape, we might add a fairing on the back side to help that out, or a fairing on the front side. You'll see this kind of thing done on the back of say, for example, 18-wheeler trucks going down the highway. You'll see these on the back, say, for example, of an 18-wheeler. It's a very square back, and you'll see these kind of pieces that are held into place with cables that are designed, they're fairings designed to reduce drag. You can contour the leading or trailing edges, and you'll see that done a lot for columns. Say, for example, if you have these columns in water, instead of having perfectly round shapes, you might turn it into a cylindrical shape so that you can reduce the drag force on that. Furthermore, for airfoils, there's a lot that we can do. So we can move the position of the maximum thickness. So as I told you, the thickness is defined as we have here. So here, this is the location of the maximum thickness. We can move that location of maximum thickness towards the trailing edge of the airfoil. And this is going to help reduce the location of separation that we have. Because here, in this case, we're going to have now the problem is as we move this location downstream, we also have more skin friction. So there's a balance because in all of these cases. And so what the good news is we'll talk more about airfoils. Most airfoil shapes have been well documented with lift and drag coefficient curves, and you can kind of make a decision based on your problem for what you'd like to do. For reducing friction drag or skin friction drag, there are a number of different things. In pipelines, one of the things that's interesting that's done is you add a thin film of water around the edge of the pipe. So you can see here you have a pipe, and then you put a thin film of water because the water has a much lower viscosity, and obviously it doesn't mix too much with the oil. And so this can reduce drag by a tremendous amount. In some cases, here in number 2, we can add V-grooves or micro riblets, they're sometimes caused. And these are streamwise oriented, and they can reduce drag as well. Sometimes you'll see them on on sails or on objects that, like, for example, skin suits for Olympic athletes. And a third example might be large eddy breakup devices. These are going to look like these kind of shapes that will allow big turbulent eddies that are big to be broken down into smaller eddies. And then finally, another example is streamlining, and it's just bending. Biological drag reduction is an example where you have streamlining or bending in things like trees or leaves. An example of that here is shown for several different types of leaf situations. So here, this is one, maybe kind of like a flower on top of a stem. Here's maybe a bushy piece of grass. Here's a leaf, and then here's a set of leaves on a stem. And the straight line that you see here, it's going up there, that's going to be in each of the cases the drag that you would see on a solid rigid body. So here, this is the velocity on the x-axis, and on the y-axis, that's the normalized drag. It's not exactly the drag coefficient the way we've defined it. This is a biology paper, and so they use slightly different terminology. But let's, for the moment, say it's drag versus the velocity. Instead of being drag, it's not exactly drag coefficient versus Reynolds number. But we'll see here that in some situations, we'll have a pretty substantial reduction as the body starts to streamline. So if we look over here, down in the bottom right-hand corner, if we pick, say, this velocity here, so this is, say, 10 meters per second. We go up here, we have, for the streamlined body, we have a a drag of, well, let's say about 10. And if we go to the non-streamlined body, streamlining body, we have to go way up here to almost 100. So it's a factor of about 100 difference. So streamlining, or like bending into the wind, if we have wind like this, the object bending into the wind reduces the drag significantly. And we can take advantage of this in our engineering applications as well. So let's take a moment to look at airfoils in a little bit more detail and understand the pressure distributions that exist over them that contribute to lift as well as drag. But now we're going to try to move over into lift a little bit. So there's this MIT Tech video that we'll look at, and we'll look at this for just a few minutes and kind of use this to understand our what's going on with lift. And I think last time it did a pretty good job getting the volume on this so that you can hear it. Hopefully it's not too annoying and loud. So we're going to move to, I encourage you to watch this entire video because it focuses on the control of the boundary layer. And very, very useful in getting a background. But we're going to start and focus on the pressure distribution over an airfoil. And we'll start here right at about minute 4.
No matter how thin the boundary layer may be, however, it has important effects.
Okay, we're moving a little bit closer. I apologize. Get just there, okay? And as usual, moved to the wrong spot. I apologize. Okay. So we are running an experiment measuring the pressure over a symmetric airfoil to start out with. And here we go.
Combinations of favorable and unfavorable gradients occur over the surfaces of aerodynamic shapes. This airfoil has a maximum thickness of 12% of the chord length, located about a quarter of a chord length after the leading edge. The model contains pressure tubes mounted flush with the surface for the measurement of the static pressure distribution. These tubes are connected to the manometer alternately from the top and bottom surfaces. When the profile is set at 0 angle of attack, the pressure distribution produces this picture on the manometer. The pressure is highest at the stagnation point on the leading edge, but decreases as the air flows aft until a minimum is reached near the point of maximum thickness. After this point, the pressure increases so that an adverse gradient exists up to the trailing edge. The profile is symmetrical, so that at 0 angle of attack, the pressure distribution over both surfaces is of equal magnitude. Increasing the angle of attack destroys the symmetry of the distribution. The minimum pressure point becomes more pronounced and moves forward, increasing the severity of the adverse gradient. This is an identical profile in the smoke tunnel. The flow tends to remain laminar up to the minimum pressure point. As the angle is increased, the minimum pressure point moves forward. The extent of the laminar boundary layer is steadily decreased until at the higher angles it exists only in the region of the leading edge. At negative angles, the upper surface gradient is favorable over most of the surface. As we can see in the smoke tunnel, the boundary layer remains laminar almost to the trailing edge. For a given lift, we get a greater length of laminar flow by modifying the pressure distribution through a change in the airfoil shape. To demonstrate this, the lift of this profile at this angle of attack will be indicated by the area of this pattern drawn on the manometer. Here is another airfoil, adjusted to give the same lift. It has the same maximum thickness as the previous one, but further aft, close to the midcord point. As a result, at low angles of attack, the extent of the favorable pressure gradient over the upper surface is increased well beyond that of the previous case. As the angle of attack is increased, the situation changes radically. Because of the geometry of the profile, the radius of the leading edge is small. As the forward stagnation point moves downward, the flow passing over the leading edge must accelerate rapidly, producing this abrupt pressure minimum and strong adverse gradients. At the low angles of attack, the boundary layer remains in a laminar state for an appreciably greater distance than with the previous profile. But as the angle is increased, the transition point abruptly moves forward, covering the surface with turbulent flow. Turbulent boundary layers thicken more rapidly and produce greater skin friction than laminar ones. Thus, reducing the extent of turbulent flow reduces the drag of the profile. We can verify this by measuring the loss of momentum in the wake of the airfoil, using an array of...
Okay, so I think this is a really nice example of what's going on over an airfoil. And here, as I have a little bit of a old note left around, this is kind of really important, because if we think about what's going on over the flow over an airfoil, you can think we have, and I'm going to try to draw this as a symmetric airfoil for the moment. We know that we have, coming into the airfoil, we have a stagnation streamline, and then going over the top of the airfoil, we have these symmetric airfoils, or symmetric streamlines. So this is our stagnation point. And given this, just to kind of remind you, like the leading edge of the airfoil looks a lot like the leading edge of a cylinder. And so if you remember, so we'll have, if we have out here atmospheric pressure, if we're far away from the airfoil, we'll have atmospheric pressure everywhere. But we have, in this case, just like when we talked about the Euler-N equation, we have some curved streamlines. And so the pressure is going to increase due to the Euler-N equation. So Euler-N, as you remember, indicates that pressure increases away from the center of curvature of the streamlines. So we've talked about this a lot, but it's important in understanding lift that's developed over an airfoil. Now, in this case, actually, it's this is a symmetric airfoil. And so in a symmetric airfoil's case, this is P atmosphere on both sides, and we're going to have the pressure forces distribution is going to be the same on both the top and the bottom. So there will be no lift generated. So there's no lift generated. So we have equal forces acting to pull up and down for a symmetric airfoil. So if we think about now, as we move a little bit farther down, so this is our point of maximum pressure, the pressure is decreasing, and when we move over to this point here, now we can start to think about local radii of curvature. And again, this is going to be the center of the curvature as we see outward moving away from the center of curvature. So this should be the region of low pressure, and then out to atmospheric pressure. So that means that as we move from the surface outward, we're going to be increasing in pressure. And so that pressure over this part of the surface is going to be subatmospheric, so low pressure. And the same thing is the case on the bottom, because this is a symmetric airfoil. And so this is going to continue to be the case as we move downstream until we get to a point where the curvature changes. So this is really important. So we can see from Euler-N, equation that we expect then the pressure to be maximum at the leading edge and then low over the top of the airfoil due to the streamlined curvature. Furthermore, over the top of an airfoil, if we have this some sort of that's not a good angle of attack. Let's get a little bit more of an angle of attack. And boy, I'm not happy with that. Let's say this is our angle of attack, so theta. We'll draw it in. So this is our airfoil. This is our angle of attack theta, which with respect to a mean wind speed u coming in. And so here again we'll have a stagnation streamline here, then we'll have streamlines going over the top and streamlines coming over the bottom. We can see then that, oops, boy oh boy, it's earthquakes this morning and it's all a disaster. I apologize. Okay, so we have something that looks like this. And so the top is the same. We have this large area over the top of low pressure. And then now we can see the streamline curvature changes here. So the pressure is now increased on the bottom. So Euler N helps explain a lot of why we have a increase in we have lift, which is, as we talked about before, the integral of pressure over the surface. The other thing that happens, as we know, is as this pressure is decreasing, the velocity is increasing. And so as a result, from Bernoulli, so sort of Euler plus Bernoulli allows us to understand that the flow is going to be accelerating over the top, higher velocity, and it's going to have lower pressure. So this is kind of a nice introductory example as to what we have why we generate lift over an airfoil. It's more complicated than this, and I highly recommend that you take the aerodynamics class to get into more details on this, but obviously this kind of gives you the basics of that. When we're talking about airfoils, we've already kind of hinted to some important terminology. So this figure here is a poorly drawn PowerPoint schematic indicating the different, very important definitions for airfoils. So you can see here we have some velocity that is with respect to the airfoil itself, and we look at the angle of attack is the angle between what we're going to call the chord line and the free stream velocity. So velocity here, that's the free stream velocity, and our chord line is defined as the straight line that's going from our leading edge. It's going from our leading edge here all the way to the trailing edge, okay? And it's the straight line going from the leading edge to the trailing edge. As we talked about before, the angle of attack is the angle between the free stream and the chord line, and symmetric airfoils, and this was alluded to in the video and what I just said, symmetric airfoils don't have any lift at an angle of attack alpha of 0. The other things that we want to look at here, so we talked about the chord line. The thickness is defined as this distance from the top and the bottom edge of the airfoil, looking at it from the side view. And then we talk oftentimes about the planform area, which is going to be equal to the span, or B sometimes we'll use, and the chord. That's the product of those two. So that's going to be the planform area of our airfoil. Textbook uses a little bit of different terminology, and I'll show that in a second, but it's important that you recognize this one as well. And here's the different terminology the textbook uses. So again, C is the chord length that we're going to have here from the leading edge, straight line from the leading edge to the trailing edge. Here, back to the other one, the span, I called it B, so here the textbook calls the span L. And the frontal area, that's going to be the projected area. And I like this figure a lot because you can see that this projected area for this airfoil section is a rectangle. You can imagine it as if you were to shine a laser or a light over the top of it, it would project this rectangular shadow. And then the planform area, just like I talked about a second ago, is this area here, which is going to be the span. It's the projected area, so it's the span times the chord length. So just some important definitions and some differences between what you'll see between our textbook and other literature when you get out into the field, especially if you're going to take an aerodynamics class or look at these other things. So this is what we just saw a second ago. This is this important video on boundary layer control. So given what we've just been discussing, let's remind ourselves what the lift force is. So the lift force is the integral of all of the force vectors that are acting on the airfoil, okay, that are acting on the airfoil in the vertical direction. We'll call the vertical direction y. So we can go ahead and if we integrate them, so here this is the pressure, we see that on the top of the airfoil, this is our suction surface where the pressure is negative. And you can really see this nicely. This is a cambered airfoil, and we'll talk about what that means in a second. But it's, so go back to it in a second, but it's non-symmetric. And so you can see it has this nice curved surface, which means we're going to have the radius of curvature for most of the airfoil is going to be inside of the airfoil, and so the pressure is going to be increasing as we go away from it, even at a zero angle of attack. So to get the lift, we integrate this pressure, the vertical component of the pressure, the whole way around. Remember, here, this pressure point is going to have a vertical component acting against lift and a horizontal component that's going to be related to drag. And for the airfoil, you can see we can also integrate the shear stress distribution, but its contribution to the lift is usually quite small. Okay, so again, we saw this in the video, and this is now illustrated here with these profiles of pressure. So the pressure is supposed to mean, if it's inside of the airfoil, that's supposed to mean that it's acting upward and it's negative. And then here, these that are acting downward, this is the pressure that's kind of our pressure surface. So the integral of this whole thing gives us the total lift force. And then, as we'll talk about a little bit later, we usually refer to a lift coefficient similar to the drag coefficient, in the sense that it's the lift force, or here this is this cursive L divided by the dynamic pressure, 1/2 rho u squared times usually the planform area. And this is interesting because you'll see again that if we plot the lift force as a function of the velocity, just like with the drag, we see this as this is proportional to u squared. So we have this u squared function. That is, it goes like the dynamic pressure. Remember, 1/2 rho u squared is our dynamic pressure. So cambered airfoils, this is a situation where we are looking at the thickness changing with the distance as we move down from the leading edge to the trailing edge. And so, as I said before, the chord thickness is from the leading edge to the trailing edge, and that's why we want to make sure that you note that the chord line is not the axis of symmetry. This blue line here, that is the axis of symmetry. The chord line is from the tip to the tail. And the cambered airfoils have lift at angle of attack equal to 0. And our naming convention here is kind of important. This is based on what they call NACA. This goes back to many years before the existence of NASA, or the National Space Administration. But here we have National Advisory Committee for Aeronautics. So this is prior to NASA. And this is kind of what you'll see here, this kind of formula. So I'll call it a NACA 0012. And the first two digits here, so what we'll see, the first digit will tell you the mean value, the maximum value of the mean line ordinate in percent of the chord. So the mean line ordinate is m. So what's that maximum value in percent of the chord? So if you have a symmetric airfoil, this is going to be 0. The distance from the leading edge to the location of max cambered is our second digit. Again, if we have a non-cambered airfoil, that's going to be 0. And then the last two digits, this is the maximum section thickness in percent of chord. So the video showed us two airfoils, one that was cambered and one that was not. The one that was cambered was certainly a NACA 0012 because they talked about it being having a 12% thickness compared to the chord. I'm not sure exactly what the cambered one was, but it would still have a 1-2 at the end. You can go online and go to NASA's website or go back to the issue grab information on different types of airfoils and the naming convention. So we were just talking about this a little bit before, and it's a kind of another way to think about the lift force. So the purpose of our airfoil is to generate a force normal to the approach velocity to give us lift for different reasons. On the aircraft, that's to lift the aircraft off the ground. And our lift coefficient is generally going to be a function of the angle of attack, the Reynolds number, and the shape. And so we will typically have a curve that will show us exactly that, which is you'll typically have one curve that shows the lift coefficient as a function of the angle of attack for different Reynolds numbers, and then for each airfoil type. So that's the shape. And as I told you, the definition is almost the same like the drag coefficient, where we have this dynamic pressure term, and then the plan form area, and then the lift force is in the numerator. Again, the lift is generated by an imbalance in the pressure along the upper and lower surfaces. This is what we talked about before, where we have this high velocity and low pressure that is acting over the top of the airfoil, and then low velocity and high pressure acting on the lower part of the airfoil. And we get this by integrating what's going on. So you can have a look at this video that I've shown here, or giving you the link to them below, and I think this is helpful for trying to understand this a little bit better. And let's see here. I want to give you this, see if I can go back to, yeah, so don't want this to, there we go. So I want to pull out of PowerPoint's preview here for a second so that I can get this YouTube video here for a second. And I'm going to copy this, and then we'll go back here to YouTube and take a quick look at this one. YouTube. And actually, I just put this in here because this is, see if I can just put in the address. This is not working, so I have to go back again. I'm not quite sure why it didn't copy, so we try one more time. Let's see, edit text. And we'll copy the text and see if that works. I apologize for slowing this down. You can fast forward through it. Okay, and this is a nice video from Cambridge, and discusses again flow over airfoils. And again, this is very similar to what we were looking at before, but I think it's important to discuss. So here, this is again using smoke and showing the faster air moving over the top of the airfoil by looking at these flashes of what's going on. That is, they're strobing the smoke as it's going over. And you can see the air that started out uniform is now going much faster over the top than it is over the bottom. And as a result, we're going to have, through Bernoulli's equation, we're going to have lower pressures on the upper surface than on the lower surface. So hopefully this kind of gives you a little bit of an understanding of how that works. And then as we increase the angle of attack, start to see this become much more extreme. You can see the leading edge where we have a stagnation point, and then as we keep increasing this, we are now going to have separation. And actually, as the separation point moves all the way up, now we have a massively stalled airfoil, and this is what happens when we have a rapid drop in lift, and we end up with, if this happens in an aircraft, the airplane will drop precipitously and rapidly. Okay, so I think it's kind of a useful, helpful way to think about airfoils. So, and lift and drag. Okay. The other way that we can think about lift, and I think I'm going to just give you a bit of a quick description of this, and again, if I do this, let's see, come on down. We'll go back in, talk a little bit more about the circulation. So lift can be thought of as in terms of circulation, this term gamma. And gamma is equal to the line integral of the velocity around some part of our object. So here I've got a cylinder, and we can get lift over a cylinder. And dl is going to be we're going to take this line integral around, just like you did in calculus. And you have these velocities that are velocity vectors everywhere. And so if we take the line integral as we go around the whole step by step, that's going to be equal to, around the circuit, because that's what this integral means. It's going to take it around the circuit. If we take the integral of the velocity dotted with the each one of these line integral terms around the edge, we will get the circulation. And the circulation times the velocity times the density is equal to our lift force divided by per unit length, let's say, or width of the airfoil or the cylinder. And so you can see in these cases where it's going to be totally parallel, we'll have an important contribution, or if you have a component that's perpendicular, then you'll have no contribution. All right, so what I wanted to do is show a short video on this that allows us to discuss this as well. So let's see if I can get back to this, and again, edit. Wrong one. Let's see. Edit text. And I think that's the easiest thing to do. If I just hit that, it should just pop right up. And now we just take a moment to, you can watch this in more detail on your own, but this is talking about form, drag, lift, and separation. So here, circulation.
The second measure of the tendency of the fluid to circulate around the curve, useful in analyzing the cost.
Sorry, let's get to it beyond the introduction.
The mathematical concept of circulation, introduced in connection with vorticity in our second film, is also useful in analyzing the cost thrust that is exerted upon certain bodies in relative motion. Circulation gamma is defined as the line integral of the tangential component of the velocity completely around a closed curve. This is the measure of the tendency of the fluid.
Now the tangential velocity component is coming from the v dot n. He's just calling it the tangential component times the L, but formally mathematically that's v dot dl.
To circulate around the curve, either in the one direction or in the other. The circular streamlines of an irrotational vortex are all lines of constant circulation, where the velocity varies inversely and the circumference directly with the radius. Now, if the velocity field of such a vortex is superposed upon the velocity field of irrotational flow around the body, say a circular cylinder, the velocity on the one side will be augmented, and on the other side diminished, in proportion to the relative strength of the circulation. The flow pattern will change accordingly. Where the velocity is increased, the pressure will be reduced, and vice versa, so that a side thrust will be exerted upon the cylinder. Such circulation can be produced in actuality by boundary layer shear around the rotating body. This is illustrated quite graphically by rolling a light paper cylinder down a miniature ski jump. Because of the rotation of the cylinder, as it leaves the jump, the cross thrust will cause it to deviate quite markedly from its normal parabolic trajectory. The same effect causes the deflection of a spinning baseball or a spinning ping pong ball from its normal course. If the cylinder is not rotating, however, oscillation of the flip pattern will cause circulation to vary first in one direction and then in the other, with the result that there is a rapid oscillation in the cross.
So this would be associated with something like the von Karman vortex shedding that we were talking about, which plays an important role. So if you throw a curveball, you get the curving that we were just seeing in the cylinder that was falling. But if you throw a knuckleball, which is a sphere without any rotation, the vortex shedding causes the ball to dance in an unpredictable manner.
This explains the tendency for telephone wires to sing in a high wind. Or it explains the whistling sound that is given off by this rod as it's swung rapidly through the air. Observation of the flip pattern behind such a cylinder.
Okay, so I wanted to just focus on that piece on circulation and how circulation is related to lift. I won't give you too much to do on circulation and lift, but I want you to make you aware of it. Again, because this is something that you will if you're interested in aerodynamics and you take the aerodynamics class, this is something that you'll need to be aware of. If we think about some real airfoils and their pressure distributions, here's an example. Let's take a look at, say, for example, the NACA 00115. So it's a symmetric airfoil that has a 15% thickness to chord, and that's defined right over here. And you can see that how does the pressure coefficient vary as we move downstream? And this is, again, going back to the video that we saw before, but you can see how we go from how we have the pressure going down and then slowly increasing back up to the trailing edge. So this is just an example of two different shapes, very similar to those that were in the video and the actual pressure distributions that exist. So lift and drag curves, I told you that these are existing for many different types of airfoils, and you can get them. You have some in the textbook for some very, very common airfoil shapes, but if you go to the NASA websites or Google NACA, you'll get, in airfoils, you get many, many, many different options. And so depending on what your application is, you can get very different types of behaviors. But the basic idea is, so on the top, we're looking at some lift coefficients as a function of angle of attack, and on the bottom, we're looking at drag coefficients as a function of angle of attack. And here we have this conventional NACA 23015 that has the shape that's shown, and it shows you the definition of the free stream velocity as well as the angle of attack. And we can see that with this airfoil, as the angle of attack increases, the lift coefficient increases until we get to some point where we get a maximum, and in this case, the maximum lift coefficient was 1.72. So that means that we have lift maximum is 1.72, and so if we know 1/2 rho v squared, CD there, sorry, 1/2 rho v squared A, if we know all of these other parameters about our airfoil, for example, if we know the planform area and we know what velocity it's going to be we're designing for, then we can get the actual lift coefficient at maximum lift. Or we can just use this curve. You could, for example, digitize this curve and pull out the actual, do a curve fit to it, and actually for different angles of attack, be able to get different lift coefficients. So the max is occurring here, so we have an increase in lift with increased angle of attack, and then at this point here, we have stall. And that's where the lift coefficient drops precipitously and pretty much all of a sudden. So it's a very important place to pay attention to. If you look at for this particular airfoil, if we look at how the drag changes, actually for very small angles of attack, the drag coefficient is very, very small, and then starts to increase rapidly. So if you're looking for a situation where you're trying to get a lot of lift and very little drag, operating it in this range between, say, 0 and say 7 or 8 degrees is really good. And then, of course, once we get to the point where we stall, the drag becomes very, very large. And this is kind of the situation that we've seen before in some of the videos, but it's worth highlighting and taking a look at, that at high angles of attack, our separation is going to occur near the leading edge, and then we have this region that's going on, and this is our vortices that are acting on us, and we have, in this case, when we have the, in this case, go back, when we have this high angle of attack, we get stall, and that means that the drag goes way up and the lift drops off immediately. Okay. We have another type of drag that's important when we talk about airfoils, and this is so-called induced drag. And this is if you have a finite length wing. So infinite length wing would mean that the aspect ratio of the, so if we go back to our definitions over here, not too far up, maybe it is too far up. So if we look at a situation where this B, so sometimes we talk about the aspect ratio, which, oh, here, I have it down here, sorry. The aspect ratio is equal to B over C, so that is that the span is much, much, much bigger than the chord. That's a situation where we're going to talk about, oops, so slowly work our way through here so that I don't zoom. Okay. So if we have a finite length wing, so that is that our aspect ratio, which is equal to B over C, is not infinite. So that is the span is not infinite compared to the chord length. In that case, what ends up happening is we have a situation where we have high pressure underneath the airfoil and low pressure above. That's basically what we're expecting. So we have our airfoil, and we have high pressure and low pressure. And when we get to the edge of the airfoil, what wants to happen is the air on the high pressure side wants to come up and jump onto the top of the airfoil, and that generates a trailing vortex. And you can, if you look online on YouTube and you look for trailing vortices, you'll see these beautiful images of, say, an airplane. This is my airplane, and you'll have these big, beautiful vortices that form. And they are beautiful. However, these induced downwash velocities that occur are a big problem, in fact, because they reduce our drag, they increase our drag and reduce our lift. And so this induced drag is important, and it needs to be taken into account as well in the type of problems that we're gonna look at. And we'll do an example problem here in just 1 second where we'll actually discuss that. All right. See if I can tap through to the next one. Yeah, so let's do an example here. So we're going to look at an airfoil example, but we'll be more specific. We're going to consider a Boeing 727 that is flying, and it's going to be flying at a steady velocity and level flight. That will make our simplifications a little bit easier to deal with. And we want to find the drag force, okay? And in looking at the drag force, we're going to say that we're told, anyways, that the airspeed of the aircraft is about 206.7 feet per second. It weighs 150,000 pounds. The planform area is 1,600 square feet, and the aspect ratio, or the span over the chord, is 6.5. And we're told that the drag coefficient at zero angle of attack is equal to 0.0182. So this will help us be able to solve our problem. So let's go back to today's notes and let's work out our example. That's our example. And as I said here, this is looking for find drag on our 727-200. It's old aircraft, and it has the weight of 150,000 pounds. It's got a planform area of 1,600 square feet. Our aspect ratio is equal to 6.5, and the drag coefficient at 0 angle of attack is going to be equal to 0.0182. Okay, and where do we get this from? Generally we can get this from a lift coefficient versus alpha curve. All right, and that will be like the curve that we just showed a little bit just a moment ago. So we're going to find the drag on our 727 at our velocity, so equal to this 256.7 feet per second. So let's go ahead and compute this. So the first thing that we need to note is how are we going to do this? So at steady and level flight, so steady indicates that we're not rising or falling, and level means that our angle of attack is going to be equal to 0. That's the basic idea that we need to get out of that. So for steady level flight, the lift is simply going to be equal to the weight of the aircraft. It's not going, the lift is just balancing the weight, and so we can say that that's the case. So this is our weight of the aircraft. And the drag, since we're not accelerating, is going to be equal to the thrust. Again, we're in steady state, so we have these nice balances that are going to exist. So from our lift and drag coefficient equations, we know that the the lift coefficient is 1/2 rho u squared times the lift coefficient times our planform area, and that, as we said, is equal to the weight. And 2, our drag coefficient is 1/2 rho v squared times, I said above that we were using v, so let's stick with v, times the drag coefficient times the planform area, and again, this is equal to the thrust. So if we take a look at the ratio of these two, so let's take the ratio of FL to FD, so there's lift to drag force. Okay, well, let's see what that is. We can start to cancel out some terms. So the 1/2s cancel out, densities cancel out. In this case, then the velocities, we're going at the speed for these things, and the areas, they all cancel out. So the ratio of the lift to drag coefficient is going to be equal to, the ratio of the lift to drag is equal to the ratio of the lift coefficient to the drag coefficient, which gives us a nice bit of information because we can use this more or less directly to determine our drag force. So the drag force is going to be equal to the lift force times the ratio of the lift coefficient to the drag coefficient. But we know from what we looked at over here that the lift, okay, that is equal to, the lift force is equal to the weight, because otherwise the airplane would be rising or falling. So this is the drag force is equal to the lift coefficient divided by the drag coefficient. Okay, so let's go ahead and find the lift coefficient. Okay, so the lift coefficient, C sub L, is going to be equal to our lift force divided by 1/2 rho v squared times the planform area. So that's going to be equal to our lift force, which was the weight, divided by 1/2 rho v squared times the plan area. We were told that the weight of this was 150,000 pounds force. We know the velocity. We were told that was 256.7 feet per second, and the area we were given is 1,600 square feet. Now what we have to deal with is the density. So here we're not told anything about it, so we're going to make the assumption that the density is equal to the density at sea level. Certainly it's not going to be correct, so I'm going to say this is not correct, but this is, we don't know anything And so for the moment, we'll leave this as the sea level density. Okay, so if we use this, given this assumption, then our lift coefficient is going to be equal to the 150,000 pounds force divided by our 1/2 times the density of air. So the density of air at sea level is 0.0238 slugs per cubic foot. And so we can put that in here, 0.00238 slugs per cubic foot. And we have our speed, which was 256.7 feet per second squared, times the planform area, which was 1,600 square feet. So if we plug all of that in, then we get a 1.19 for our lift coefficient. So we're looking pretty good. We know right now what our weight is, and we know what the lift coefficient is, and we have some idea of what's going on with the drag. And this is where we're going to introduce a small bit of instruction that we didn't talk about yet, but we said that we have this so-called induced drag coefficient. So our induced drag. And remember, this occurs if we have a finite wing length. So our aspect ratio that we've been given is 6.5, so this is certainly finite, but how important is it? Well, the way that we typically compute the total drag is we have our drag coefficient is going to be equal to the drag coefficient for an infinitely wide body at 0 angle of attack that we're looking at now, plus the drag coefficient due to induced drag. So the way the induced drag coefficient is typically calculated is, again, another non-dimensional kind of parameterization. So it's the lift coefficient squared divided by pi times our aspect ratio. So this comes from dimensional analysis, like you've done with Buckingham pi, dimensional analysis, and then experimental data. Experimental data. Okay, so given this, we could go ahead and compute what we have. So we can say that the drag coefficient, the total one, is going to be our CD0 plus CL squared over pi times the aspect ratio. And if we plug in what we have, so we know that we have our drag coefficient at 0 angle of attack was given to us as 0.0182, so 0.0182, plus our lift coefficient, which we just calculated as 1.19, so 1.19 squared, divided by pi times our aspect ratio, which was 6.5. And when I calculate this, I get 0.0877. And this is our total drag coefficient. Okay, so now we can go back up to our equation that we had here. So this is probably the most important one. So now we do know the weight, we know the lift, and we know the drag coefficient. So we'll go ahead and compute the drag force based on this equation that we have. So the drag force is now going to be equal to the weight times the ratio of the lift to, lift to the drag coefficient. And I apologize here. I think I typed that incorrectly when I was cranking through this too fast. So we have just show you what my error was so that you can see. So I had lift, of course, divided by the drag is CL divided by CD like we have there. So we should have drag, as we do the cross multiplication, should be equal to the lift coefficient divided by, the drag coefficient. Let's bring this over here, right underneath it. So we have that the drag is equal to the lift times CD over CL. Sorry about that. So we'll go ahead and swap this in. Easier for me to do than you. So we have the drag coefficient over the lift coefficient. Drag coefficient over the lift coefficient. My apologies. Okay. So we'll go down here, and then we have our drag coefficient divided by our lift coefficient. So this is going to be 150,000 pounds times the drag coefficient, which is for us going to now be 0.0877 divided by our lift coefficient, which was 1.19. And then that gives us a drag force equal to 11,060 pounds force, because this was pound force, and everything over here was on the right-hand side. This is all non-dimensional. So that's our drag force. Okay, so a nice example to work on for understanding this a little bit better. Last couple things that I want to discuss before finishing up. So here's our, in addition to our airfoil example, we'll also have, discard those for the moment. I want to move on to just finishing up. We only have 2 slides left. Reminding what the breakdown of drag looks like for lifting and non-lifting bodies. So non-lifting bodies, these are going to be things like our bluff bodies. Our total drag is going to be this combination of the skin friction drag and the pressure drag. But if we have a lifting body, our total drag is going to be the skin friction drag plus the pressure drag plus this new induced drag that we just discussed and did a small problem on. Now, the ratio and the percentages of these are going to depend a lot on the actual shape of the bodies. One last kind of fun piece of information that I like to talk about related to aerodynamics is the so-called Coanda effect. So this is the tendency of a jet to stay attached to a curved convex surface. And it's a very interesting and kind of phenomena. Again, there are a couple of experiments that I like to show in class, like our levitating plate experiment that I don't get to show to you this semester, but I'll discuss this anyways. Here on the left-hand side, we have this jet. So here we have a wall. Think of it as like a step. And we're blowing air along the edge of this. So think maybe you have the exit of my leaf blower, and it's blowing air here along the surface of a step, maybe an edge of a table, and then the table ends right here. And so the air flow is very high near the surface and then decreases out to the 0 velocity above the wall. So let's say this is y and this is your velocity u. So you have this little wall jet, we'll call it. Wall jet. And what's going to happen? So as the jet gets to the edge of the wall, we have a very sharp edge. And what do you expect to happen? Well, I think at this point, you should expect that you're going to have a very difficult time for this flow to come around this corner. So it's going to separate, and the separation means that the jet is basically going to continue on without almost any knowledge of the wall. So it will jump out, and there'll start to be what we'll call entrainment. So a little bit of entrainment coming in, and that way we don't exactly have this sharp profile over here, but as the jet goes out, kind of doesn't see the wall stopping, but very slowly air is allowed to freely entrain still air. And so if our original profile looked something like this, now, and out to the top, now we've added slow air, and it will continue to diffuse outward with time, because the peak velocity will decrease. All right, so that's what's going to happen at the edge of a step. What happens if we restrict this entrainment? And there's also, by the way, entrainment coming in from this side as well. What if we restrict the entrainment at the wall? So what we'll have in this case is what a Coanda jet is. And so if we have a type, so those are my same kind of things where we have these entrainment going on. now what we're going to do is we are going to slowly curve the surface. If we slowly curve the surface, one of the things that you know is that this is going to be a region of low pressure, and this is going to go to atmospheric or high pressure from our oiler end. So this would be low to high. And so that's going to want to suck the jet onto the surface, and that's exactly what happens. And then part of this is a result of the fact that air cannot be entrained from this side, and so we have a bit of a low pressure phenomena going on, and so the air will continue to stay stuck to the side of this surface. And you can this is used in all kinds of aerodynamic control processes where you want to help avoid separation. And this is called the Coanda effect. One sort of way to kind of illustrate this is if you go and you turn on a faucet, so and then you allow, so if you have in your sink and you have your faucet coming out, you have some water coming out of it. If you, I don't know, you stick your finger in here, so this is your finger or a cylinder. Watch the water go over the top of it, and from the side, what you'll see is that the water will come in and then move around the outside. And that bending that you'll see is this so-called Coanda effect, and again, very much related to our Euler end effect. So if you didn't like Euler end, you should like Euler end. It's a very exciting phenomenon. It allows us as engineers, mechanical engineers, to be able to control flows in different ways. Okay, so that is the end of today's lecture. And please don't forget to do your quiz today. And next week, we'll have one more main lecture, and then we will have an exam review.